attended this community of practice on sustainable concrete. So I'll just give a bit of an introduction as to what the community practice is, what it means, and I guess what we like to kind of take out some of these webinars that we have. So the community of practice, specifically this one, is around sustainable concrete. We aim to bring together both industry experts as well as our academics and researchers just to understand, I guess, the advancements in concrete, in cement, I guess, where we're going, what we're currently doing, things that are likely to change as we move towards, I guess, a more sustainable country, a more sustainable world, I guess, more sustainable civil materials. So we like to, I guess, use this kind of platform just for educational purposes, no commercial references. This is merely just technical based, just talking about some of the challenges that we see in the industry, some of the challenges and the gaps that we see in the academic world, and also how are we progressing. What are we focused on as an industry, and I guess where we should be putting our focus on in order to achieve our 2030, our 2050 targets. I think, like myself and like everyone else on this webinar, we have, there's a big push on, I guess, how we reduce our embodied carbon in our, I guess, in our industry. And so I would like to use today as a way in which we can look at sustainable infrastructure. So the agenda is for today, we have two specific speakers, Harish from Transport New South Wales and Professor Vute from UTS, who will just talk to us about sustainable infrastructure, what that means, I guess, looking at standards, looking at, I guess, progression in regards to what we're currently doing and what we intend to do in order to meet our targets. So I guess the main purpose of this specific community of practice on sustainable infrastructure, we wanted to talk about some of the changes that are occurring, some of the changes that are likely to occur, whether that's looking at specific design concepts and how customers are asking for specific different, I guess, specifications, I guess where we're moving towards and what our expectations are. So without further ado, I'll go ahead and I will introduce our first speaker. So just a little bit of a background on Harish. Harish is currently the Director of Civil Engineering within the Advancement of Technology Services Unit of Infrastructure and Place Division of Transport for New South Wales. He is responsible for providing technical advice to project teams, delivering a multi-model projects, delivering strategic projects, and the development of standards. Harish is the Transport in New South Wales representative for Smart Creek CRC, and he is involved in the development of low-carbon concrete mixes, including recycled materials and sensors, and digital twin-based asset management technology. Harish has over 25 years of experience working on projects in many different countries. His knowledge expands to many elements of project lifecycle, including feasibility, concept, detailed design, construction, commissioning, and operation. So please welcome Harish. The one thing that I would say is please refrain from asking any questions. I'll let Harish talk and then Vute, and then at the end of both of the presentations, we will have a big open discussion. Feel free to ask questions. The manner in which I would prefer everyone to do it is either to raise your hand or just add a comment in the chat box, and then you're welcome to add the ask the question to whoever you are directing it at. So once again, welcome everyone, and I hope that we get a lot of I guess interesting knowledge, facts that we'll be able to, I guess, talk to each other about in this specific meeting. Without further ado, I will hand over to Harish. Thank you.
Thanks, Olivia. I'll try to share my screen. Please let me know if you can see it. You can see it well?
That's perfect. Thanks, Harish.
Okay. So thanks, Olivia, for your kind words. I think good afternoon, everyone. Today I'll talk about a sort of high level decarbonization, where I'll touch on both need and strategies for decarbonization of concrete, to be very specific. So before I go any further, I would like to acknowledge the traditional custodians of the land. Today I'm speaking from Ashfield, which is land of Wangal people. So I acknowledge Wangal clan of Yura Nation and pay my respect to the traditional custodians of the land on which we meet, especially elders past and present, and acknowledge other Aboriginal people here and their respective cultures and nations. So this is the content of the presentation is like in three parts. One is I'll talk about in general decarbonization, and then I'll drill down into why decarbonization of concrete is required, and then how Smart Creek CRC research projects help with this decarbonization. So first is about need for decarbonization. As all of us know that signatories of Paris Agreement need to contain the global warming to 2 degrees Celsius about above pre-industrial level, whereas the preferred level envisaged is 1.5 degrees Celsius. What sort of got me a bit concerned when I read this IPCC 2021 report, which sort of envisages that there's a 50% likelihood of exceeding 1.5 degrees Celsius in near term. So that means we need to do something to contain the global warming. And it's a bit of buzzword, global warming or carbon dioxide emissions. So I try to establish a linkage between that. So if you look at the picture on the right, which is taken from IPCC 2021 report, it essentially establishes the relationship between global warming and the carbon dioxide emission. So I think without getting into the nitty-gritty of how the graphs and curves and sectoral emissions, I'll probably try to contain myself to construction sector related. So means Australian construction sector is responsible for about 18% of Australia's greenhouse gas emission. So that means this is a critical part of net zero equation. So this is the Australia's or Commonwealth government emission long-term emission reduction plans, and there's a like a four streams and lot of initiatives. So I just highlighted in red box the initiatives which are related to the construction sector. So for example, low emission steel and aluminum is very much essential for construction sector decarbonization. Similarly, probably one of the ways we can sort of encourage decarbonization is by incentivizing the businesses. So I guess probably I don't intend to read every box, but this is sort of draws from the like top to bottom so that we have like bit of context setting. So drawing on this Commonwealth government plan, transport has these sub plans or develop these plans as part of its decarbonization policy. And you are welcome to read at your own leisure these things. I have just put some snapshots so that you get the title and name of the documents, and they are available publicly. But essentially, the policy is to drive both operational and embodied carbon to net zero by 2050. So, to going a step further, recently Transport published the recent version of policy included transport commitment. So transport is committed to, I think there's a bit of background noise. Olivia, will you mind getting people
I fixed that. Sorry,
Yeah,
go ahead.
thank you. Okay, so transport's commitment is to sort of achieve net embodied carbon emission, net zero for embodied carbon emission by 2045, and net sector-wide net zero emission by 2050. But this will be done in a sort of a staged manner, and this slide highlights the stage plan. So I don't intend to go line by line and read it. I guess probably the message is we are trying to do this to achieve net carbon net zero in stages. Now I'll talk about a bit more which engineers like, how we can achieve decarbonization of concrete. And I think the first logical question is why concrete? So I guess concrete, if we look at all the construction material, concrete is one of the lowest embodied carbon material if we compare with other materials like steel and aluminum. Whereas we use a lot of concrete, and that's why it becomes a critical material. So there are some numbers here like 29 million cubic meter of concrete we use in Australia. And if we focus on the structural concrete, the carbon footprint of concrete is anything between 230 to 615 kilo per cubic meter. So if we combine the two, about 12 million ton of CO2 is basically associated with with concrete. And if we look at the picture on the right, so out of all these materials, Portland cement is the highest emitting material in concrete. Though we use only 12 to 15% of cement in concrete, but it is responsible for about 90% of CO2. So that's why most of the strategies revolve around the eliminating or reducing the Portland cement. I would like to remind, if people still remember, the VDZ report published in 2021, again by the effort of Cement Australia, CCAA, and SmartGrid CRC. That sort of highlighted a very interesting fact that by improving the concrete technology, we can reduce the carbon footprint only by 13%. So means that include SCM and geopolymer and whatever we say. And the impetus was about the developing or probably improving the design as an overall, which was attributed 21% potential reduction. And then carbon storage was another 21%, another 33%, if my memory is still correct. And then 6% was attributed to recarbonization of the concrete. So I think with this background, this is sort of my version of breaking down VDZ report. So when I thought about it, I said, what we are doing, what additional we can do. So if we start from bottom to top, so first is cement. So cement is the most of the emission is related to the process CO2 and fuel CO2. Fuel CO2 is about 26%. And what currently is being done is mostly we are using alternative fuels, which are sort of drawn from waste stream material. Where we need to go, probably we need to inject more and more greener fuel, hydrogen, wind, solar, and probably ethanol could be another addition to this sort of stream. Then at the moment, the impetus is partially replacing the cement with SCM. Everybody talks about more SCM. But I guess probably we need to embrace new zero cement technologies like geopolymer concrete, sulfur concrete, LC3, just to name a few. Then going up in the cycle, the next one is water. At the moment, we use recycled water, steam curing, but probably we need to go to carbon cure type of technology where we inject carbon dioxide both in the while batching and also during the curing process. And advantage of this is, first thing, it acts as it sort of locks the carbon dioxide into the concrete, so it is basically like support the carbon storage. And some of the papers have reported that up to 20% of strength improvement can be achieved by injecting the carbon dioxide. So that means it has got a dual benefit. Then moving up the chain, probably recycle means we try to put more and more recycled content into the concrete. But I guess that can work to certain extent. Probably we need to think about this 21% potential reduction is like design improvement. So things like ultra high strength concrete, which can reduce the material, total material. So that will include aggregate and cement. Aggregate and cement in the quantity or the overall quantity number, but per unit cement may be more. So I guess another thing to note, none of these initiatives on a standalone basis can achieve a net zero. So that means we need to wisely develop strategies for each project to combine multiple of these initiatives to sort of suit the project so that we can have both best of both worlds. We can have best outcome for the project as well as best outcome for the sustainability and net zero. Now I'll probably try to link up that circular diagram with whatever project transport is involved with the smart grid CRC. So if we just see these 5 projects on the screen, so they can be potentially categorized into generating new aggregate by using recycled material. For example, recycled craft glass, uh, plastic waste, mine waste. So they were not conventional aggregate. Then we we sort of get into like manufactured aggregate. Then the other important thing is using, say, bottom ash. We use fly ash a lot, but bottom ash is probably another potential material that can be used both as aggregate as well as the uh, SCM. And then we are also trying to develop some new stream of SCMs, which is, for example, this manufactured amorphous silica. This is an interesting project because this project comes out of the carbon dioxide injection process. So obviously its source is carbon dioxide injection. So that means it is intending to the overall process is intending to sort of intending to absorb and store the carbon dioxide. And and then byproduct is amorphous silica, which we are trying to use in concrete as both as SCM as well as the aggregate. And and then furnace bottom ash, we are trying to develop a process as part of this research by which the furnace bottom ash could be used as SCM. Then we have recently started a project of using calcined clay. At the moment, it's intended to be used as SCM, but it could be used as a full replacement of cement as well. Another thing which is not on this slide because this is project in development process. We are trying to develop a project for developing design guide and specification for ultra high performance concrete to be used into sort of infrastructure. So obviously that will support the decarbonization. Then these are the couple of interesting projects, which is first one, probably Professor Vute will talk a lot about it in his presentation, so I don't want to double up. But intention is to develop a framework for selecting low carbon concrete. So we are not trying to stop at current generation of concrete mixes, but we want to go into future mixes as well. Then this one is another interesting project which sort of draws on potential 6% recarbonization from the envisaged by VDZ. So this project is having a tier 2 calculation about CO2 sort of absorption into the concrete. So I think this will be a good fit into net zero solution. So I guess probably in short, we probably I discussed about various sort of transport initiatives. and policies and commitments which support net zero. And then probably I could explain that transport collaboration with the smart grid CRC is likely to generate new material, new SCMs, and also underpin the dematerialization. So I think that's it from me. And back to you, Olivia, for sort of managing the rest of the show.
Perfect. Thank you so much, Harish. Really interesting work. It's good to know what Transport New South Wales is doing currently and where they see, I guess, the next stages to, I guess, this industry collective goal in regards to how we're going to reduce and decarbonize our industry. I will just introduce our next speaker, Professor Vute. Will be discussing the project that Harish mentioned in regards to a project with Smart Creek CRC as well as Transport in New South Wales. So Professor Vute is a civil engineer from UTAS. Dr. Vute is currently a professor of concrete engineering at the University of Technology, Sydney. He has worked as a bridge design engineer, a quality control and structure engineer in Singapore before joining the CSIRO in 1988 and CCAA in 2006. Dr. Vute has conducted extensive R&D in the use of industrial byproducts and manufactured sand and concrete. He's the director of UTS Burrell Centre for Sustainable Building, Research Director of Smart Creek CRC. Please welcome Dr. Vute. And once again, all the questions for both Harish and Dr. Vute will be at the end of Dr. Vute's presentation. Over to you, Dr. Vute. Thank you. I believe you're on mute. That's okay. Thank you.
Yes. Thank you, Olivia. Now you can hear me. And good afternoon, everyone. I will go straight into my part of the contribution to this community of practice. Let me share my slide with everyone. Okay, can you see it?
Good to go, thank you.
Okay. My brief presentation will stress on performance-based choice. In other words, it's all about concrete that will deliver the performance that is required for whatever application that you have. But just before I do that, I will talk about, in general, carbon management, which basically Harish have highlighted many aspects of it. For me, there are three essential tasks to decarbonize our infrastructures. The first is to optimize our structure design. We can do so much without design, so as to optimize the performance and also the use of the structure materials, and in this case, concrete, in our design. And that is item 2. Now, once that's done, it's a matter of selecting low carbon concrete that will perform according to what is required in the project itself. My definition of low carbon concrete is very simple and straightforward. Low carbon concrete is user-friendly type of concrete with good workability, constructability, and safety in handling and so forth as well. It must have the mechanical and volume stability properties that are required for the structures in question. And finally, it must have the durability properties related to the design life required for that particular structures in the particular exposure environment in question. Now, all these must be achieved at the lowest possible embodied carbon. So very simple definition of low carbon concrete. Now, if we look at the contribution of embodied carbon of the concreting materials, which I think Harish have highlighted. Of course, Portland cement is the one with the highest embodied carbon per kilogram for the binder, I guess. Apart from that, the fly ash, you can see the fly ash has a much lower embodied carbon, and so is slag. So the question is, how can we make better use of some of this SCM, supplementary cementitious material, in the concrete production? Now, if you look at what I highlighted at the bottom, are the embodied carbon of a range of alkali activator that are used to produce geopolymer concrete. So in my brief presentation, I would look at concrete with high SCM on the one hand, and also potential use of geopolymer concrete as well. And all that depend very much on basically the formulation of the different material which resulted in the embodied carbon of the concrete. The range of key performance, I stress performance, and that's just the detail of what I have mentioned earlier. In the case of workability, constructability, apart from the slump, pumpability, and so forth, depending on the application, you may have early strength requirement for precast or early strength requirement for in situ casting as well. So those are very important, apart from the range of mechanical and volume stability properties that the structure engineers would require for his design to work. And last of all, durability properties. And apart from the normal exposure, either a carbonation-induced corrosion issue, chloride-induced corrosion issue, or sulfate, don't forget about the possible deterioration mechanism due to alkali-silica reactivity, and also the possibility of delayed ettringite formation, which may affect concrete that may be killed at very high temperature. Now, if we look at a typical specification for concrete, I use the example here of transport for New South Wales B80 specification. And in particular, I just choose a particular exposure of B2. What you can see is that the specification consists of two parts. One is that of the prescriptive requirement in terms of cement content and water to cement ratio, as well as the performance-based requirement in terms of strength grade and in this case, maximum chloride increase coefficients, depending on the specific test method that are required. I use this particular specification to then show you that in the area of the use of SCM to produce blended cement concrete, the influence of the type of binder is so high insofar as it affects the embodied carbon of the concrete in question. In this case, if you look at the 28-day strength, for instance, you can clearly see the influence of concrete with either just GP cement, 30% fly ash, or the 50% slag on the embodied carbon, respectively, of the concrete that will meet a particular strength grade requirement. In this case, it happened that the slag came up, I guess, best with the embodied carbon just around the 220 to 30 kilogram carbon dioxide per cubic meter of concrete. Now, apart from strength and mechanical properties, we also require durability properties. And in this case, again, I show you the example of the influence of the type of binder on chloride diffusion. And again, what sort of embodied carbon that would result from the choice of particular binder that you produce your concrete. In this particular case, if we look at the diffusion of around diffusion coefficient of around 3.5 times 10 to the minus 12 meters square per second, again, slag seem to be, the 50% slag seem to be the best among the three binder systems that we show here. At the end of the day, though, you need to choose the best concrete that meet all your performance requirements. And I'm merely show you two performance requirements here, 20-day compressive strength and chloride diffusion. And that's basically the combination of the two data set that I showed you earlier. So in this case, if you choose the 50% slag to produce a grade 40 concrete, basically it would demand about 230 kg of CO2, and that particular corresponding 50% slag mix will give you a diffusion value of around 1 times 10 to the minus 12 meters square per second, well below what is specified. So in this example, is the strength that basically control the choice of your low carbon concrete that you would need for that particular exposure conditions for those particular applications. If this happened to be precast, there may be the early strength may be the control factor. And the point is that you need to look at all the performance and the respective embodied carbon of the concrete that you used to come up with concrete that meet all those performance requirements. I'll now quickly go through some of the data that we have collected for geopolymer concrete. And I'm sure most of you are aware that in late last year, Standard Australia have released the technical specification TS199, which covered the design of geopolymer and alkali activated by the concrete structures. I think this particular technical specification basically would support the greater confidence for engineers to start looking at the use of geopolymer concrete more seriously. And I summarize basically the type of aggressive environment that has been defined and also what type of durability concept that are used in that particular technical specification 199. And I would also show you just a couple of set of data, show you the relationship between the different geopolymer concrete and a range of other concrete with SCM on the embodied carbon with respect to strength and some durability. Just an example. In this case, the circle with the darker color, whether it's black or blue, represent the geopolymer concrete. And you can see that for the sort of strength we are looking at, geopolymer concrete would give a much lower embodied carbon than the sort of concrete that I've just shown you in terms of concrete with high SCM. So it's a very good start in terms of strength. Now, if we look at the durability, and in this case, in terms of chloride coefficient, again, but this is to not test 043, which is an accelerated chloride diffusion test method. You can see that for the sort of level that we are looking for, very low diffusion coefficient of around 4 to 8 times 10 to the minus 12 meters squared per second, only one type of geopolymer concrete likely to give you the performance, and that is the blue color, and that represents geopolymer concrete with more than 50% slag. Whereas the other concrete, the one with lower than 50% slag, although give the strength that you may need, but give a much higher chloride diffusion value, and therefore will not satisfy the durability requirements. So that's the challenge. Again, I relate the two performance into one. And basically, what it says is that yes, geopolymer concrete, certain type of geopolymer concrete does have a very good potential to be used with much lower embodied carbon than the concrete with high SCM that we have. So I won't conclude. I merely want to emphasize that you need good performance data to enable you to select the binder system or the concrete to produce the best low carbon concrete for your applications. And this is where I will end my presentation and hand it back to Olivia.
Perfect. Thank you, Vute. I think it's really good that you started off your presentation with your own definition as to what low carbon concrete is, because I know in the last few weeks that's been quite a topic in regards to how do we even define low carbon concrete, because in my opinion we are already achieving low carbon concrete. So I think it's really good to look at what are we currently doing, what can we do to improve it even more, and what does the future hold in order for us to, as I keep saying, achieve our 2030 2050 goals. Okay, so once again, I'd like to thank Harish and Vute again for your presentations. Really interesting work. So now is time for questions, commentary, just a bit of a discussion. So as I mentioned at the start of this webinar, if you would like to ask a question, you're welcome just to raise your hand and then unmute yourself, or you could ask a question in the chat section. And as most webinars or seminars, people are quite hesitant to be the first person to ask a question. So I'll do the honors and I'll ask the question to both Harish and Vute. And then, like I said, feel free to add any comments in the chat or just raise your hands if you have any questions. Okay, so first question, I'll kickstart this. I have a question for yourself, Vute, and I believe Harish will probably be able to answer this also. But Vute, you spoke a lot about geopolymer, and I know that's quite a topic that people have done a lot of work on in the last decade, if not more. So my question to you is, when we look at geopolymer concrete, I understand it has its advantages. I can definitely appreciate that. But if we talk about, say, for instance, the closure of power stations and the scarceness of actually obtaining slag, so you're looking at your main materials like your fly ash and your slag, do you really think that it is a viable option in regards to significant improvement as a means of reducing the embodied carbon in the industry? Or do you think it's more so for small applications?
Thank you, Olivia. Well, firstly, fly ash and slag are so important for the present-day concrete, I guess, where we try to use the right type and the amount of SCM into our concrete mix design to reduce the embodied carbon, as I have demonstrated. Of course, we do worry about the potential shortage of, in particular, of both actually, fly ash and slag in Australia. But I think if you look at it seriously, I think we would still have fly ash for the next 5 to 10 years. Apart from the quality fly ash that we at the moment accept to be used for concrete application, every day we also produce what we call run-of-the-station fly ash, which we are dumping at the moment every day. That fly ash actually have the potential for many applications, including the use for the production of geopolymer concrete, as well as many other applications. I guess in a way, Australia been spoiled by the fact that because we have so much fly ash, we have been very choosy about the top quality fly ash that we want, without looking at the second rung of quality of fly ash. So I still think it's a potential that we need to tap in for the next 5 to 10 years. Now, at the same time, of course, there are many developments which Harish have highlighted in alternative SCM, as well as there are technology that I am aware that Cement Australia, for instance, is working on trying to reduce the embodied carbon of cement as well. But in the next 10 years, I still see the future of both concrete with high SCM and geopolymer concrete.
Perfect, thank you, Vute. I definitely agree. I think we're definitely going to still have fly ash in 10, 20 years. I know a lot of people question whether or not that is the case, but I think if we really think of it in regards to electricity and power, we still need something to keep these lights on. And I don't think they're going to turn that off tomorrow or the next day. So I definitely agree that we're definitely going to have fly ash in 5, 10, 15 years. Okay, so we're having a few questions rolling in the chat. So first question I have from Glenn is the CRC, so Smartcrete, planning to look at any research projects injecting CO2 in concrete?
I guess I put on my research director hat of Smartcrete CRC. Smartcrete CRC objective is really to support our industry drive towards sustainability. Now, it means that any project that we support must meet the objective of Smartcrete CRC, as well as strong support from industry. So to me, it's a question of whether there are industry that prepare to invest in the development of this type of technology to support our industry. So in a way, I'm putting the question back to our audience and our industry in general.
Okay, thank you. Thank you, Vute. A question for both of you again. I think I'll just start with Harish here. What are the knowledge gaps in low carbon concrete that would need to be applied would need applied research? It's a bit of a broad question, but
yeah, I guess I touched in my presentation, part of it is basically the low carbon concrete doesn't mean a sort of concrete mix as such. It basically should be outcome focused definition where you can achieve the lowest carbon for the project. So even, for example, ultra high strength concrete, that may use more Portland cement. But if it sort of brings down the carbon footprint of the project as overall, I think that will be a good outcome. So I think that's where probably sometimes the definition of low carbon concrete will get tangled into the more SCM or no cement. But I guess it should be more like outcome focused definition where we achieve the best for the overall project rather than individual component.
Perfect. Vute, did you have any additional commentary or?
No, I think that's I think what both of us basically would love to see the optimization, and that may also include the construction itself. And in the case, one example, for instance, the use of precast, which usually mean concrete with high early string and therefore high cement content. But if it enable improvement in productivity, in the performance of the structure itself, overall, that's what decarbonized infrastructure is all about. We must look at the design, must look at the use of the selection of the material, as well as the construction to deliver the outcome that we want.
Perfect. Thank you, Vute. And I just have one additional question from myself before I go back into the chat. Harish, you spoke about LC3 cement, and I know this is something that I hear a lot of in different seminars and webinars. So my question is to you. I understand that LC3 cement is a developing, I guess, method in which we can reduce embodied carbon in cement. But do you really think that we can obtain a low enough embodied carbon if you're comparing it to, say, a 70-30 slab mix, considering the fact that you have to mine a green field and also you have to calcine the product, despite the fact that the calcination temperature is lower than what you would see in cement manufacturing? But do you really see, I guess, the reduction being quite significant?
I think, Olivia, it's an interesting question, and that's one of the sort of like closing remarks I said is not one technology fits all. But I guess as far as LC3 is concerned, it brings down calcination temperature from 1450 to 850. So that means half fuel means half temperature, so roughly half fuel consumption. And if like 26% of calcination process fuel, calcination process emission is fuel related emission, so straight away you can reduce that to 13%. So that's a quantum shift from the current scenario. Now it's a evolving field. We still have not seen how this LC3 or calcined clay can be combined with other materials. For example, how LC3 or calcined clay can be combined with fly ash. And if you imagine, like currently, if we look at, say, like Wood has presented already his graphs, we can get probably 50-60% reduction by maximum use of fly ash and slag. So if we use the same equation and just replace Portland cement with LC3, then that 50-60%.
You call me for the meeting, is it? Oh, I do. Okay, yeah. Just we can have.
So that 54, that whatever percentage, X percentage will come down further. So I guess it's more like an incremental reduction rather than a quantum jump from A to B. I think that's where probably the argument lies. There's no one solution is likely to fit all.
Perfect. Thank you so much, Harish. And another question for both of you, that's from Liam. How can we provide certainty to consumers of concrete, for example, Transport New South Wales construction businesses, for new materials without long history of use? If we are focusing on the performance-based criteria for low carbon concrete structures with new technologies. So I don't know who wanted to start, Harish or Vute, either one of you.
I guess, Liam, is a bit of evolving question, and I guess there's no perfect answer for this. And I guess that's where transport investing a lot of energy and time and money into the research to basically understand these new materials, how they are going to perform in relation to the existing portfolio of materials. And I guess there's a role by Standards Australia to be played. Like a good example was TS199, which Professor Wood presented. I think one of the impediments to the adoption of geopolymer concrete was the standard support. So I think as we expand the material portfolio, most likely Standard Australia is also going to include these materials in some shape or form, and that will probably stimulate the sort of market and also give the designers and constructors a bit of confidence in terms of adopting these new technologies. Professor Wood, you want to add anything?
Yes, I think, well, firstly, obviously, it's a challenge. Liam, as I pointed out, one of the three key properties or performance that we require is that of durability. And durability is possibly one of the hardest performance that we can verify, I guess. Now, the answer, I think, lie in the understanding of the fundamental of the material in questions. I'll probably give you an example. The work that, in fact, Liam, you and other colleague at UTS is working right now is the question of, say, alkali silica reactivity. Now, a lot of the exerted test methods were developed for conventional type of concrete, I guess, the Portland cement concrete or the blended cement concrete that I mentioned. And the method involved increasing the environment for the reaction to occur, either by increasing the exposure surface area of the aggregates, or increase the temperature, or increase the availability of alkali that may trigger the alkali silica reactivity. Now, if you want to look at geopolymer concrete, for instance, whether the use of geopolymer concrete with ASR, alkali silica reactive type of aggregates, how would you test it? Now, the work that's been done in Australia so far have simply used the method that's been developed for conventional Portland cement concrete. Because we understand alkali silica reactivity, we understand the chemistry of Portland cement concrete, we understand the chemistry of geopolymer concrete, we need to then put that understanding into the type of test that we do to accelerate the deterioration process in question. Geopolymer, for instance, have very, very high alkalinity in the first place. And therefore, to use it in an AMBT test, for instance, is, to me, won't work, because it already have very high alkali in the system itself. So the AMBT, for instance, we immerse this mortar in highly alkali solution to accelerate the reaction. So I hope that example help answer that very question. We need people who understand the fundamental of the material in questions and the deterioration process associated with certain exposure conditions to try to understand how a new material would perform. Sorry, quite a long answer, Olivia, to a short question.
That's okay. That's perfect. And just one last question, just for the sake of time. This question's from Harry. What is the most energy intensive stage in the actual unit operations of the manufacture of concrete with any low carbon embodied ingredients?
Can you repeat that question again?
Yeah. I think, Harry, you're referring to the most...
So concrete production, not cement production.
No, specify concrete production, but I think the person meant to say cement production, because I think, as Harish already mentioned, a lot of the embodied carbon actually comes from the cement aspect. Even though we might only have 12 to 13% actually in concrete, that's where a lot of the embodied carbon comes from. As Harish said, around 80% actually comes from the manufacturing of cement. Because when it comes to the actual production of cement, you have your limestone, in which you have to calcine. So that's where a lot of that comes from. I think someone is not on mute, but that's okay. Did Vute or Harish want to add to that at all? I believe it was more around the embodied carbon of cement manufacture.
I guess, Olivia, you are best placed to talk about cement. You know cement better than probably at least me. I can't sort of say on behalf of Wood, but I guess you have correctly sort of said. I think if the interpretation of question is that, then probably you have given the answer. And
yes, that's okay. Just for the sake of time, I know a few more questions are rolling in. I would just like to thank both Harish and Vute again for their presentations. Really appreciate the knowledge sharing. And thank you everyone who participated in the questions and the discussion. Please feel free to either email myself or Jana or Professor Vute, or even, if that's okay, Harish, directly if you had any questions following up from this webinar. Once again, thank you all for joining this community of practice, and we'll hope to see you at another community of practice very soon. Thank you all.